When physical forces act on a solid material, like severe stress, the resulting deformation happens across a continuous reality. Every millimeter reacts. But finite element analysis cannot compute an infinite number of continuous points. To solve this, the mathematics require us to sample the physical state only at isolated discrete coordinates known as nodes. Calculating values only at isolated nodes creates a literal blind spot. We have zero concrete data in the empty space between them. To cross this void, we use interpolation functions, mathematical approximations designed to predict the field based on limited nodal data. Without a precisely derived interpolation function, your discrete nodal data remains a collection of disconnected dots, entirely useless for simulating real-world physics. To build this mathematical bridge correctly, we apply a specific weighted residual approach known as the Galerkin method. The Galerkin method imposes a strict initial rule. Any trial function we design needs to satisfy only the essential boundary conditions. In a one-dimensional model with a single degree of freedom, an essential boundary condition is simply the known physical value exactly at the nodes on either end. These end values represent the only fixed data points we possess in the local system. Every subsequent calculation must align with these known quantities. Our objective now is to engineer a continuous function that perfectly locks into these fixed boundary values, regardless of how the material behaves in the middle. We begin by limiting our geometry to a one-dimensional element, where we only care about a single degree of freedom per node. We establish a local coordinate system. The first node sits at an x-coordinate of 0. The second node sits at an x-coordinate equal to the element's total length, L. Knowing only these endpoints, our simplest possible guess for a continuous field between them is a standard, general linear polynomial. In this equation, x is our spatial coordinate. The terms a0 and a1 are unknown coefficients. We need to find them. To solve complex structural systems efficiently, keeping equations in their standard algebraic form is too slow. We must translate this polynomial into linear algebra. We separate the elements by placing the spatial variables into a row vector, which we denote as h of x. The unknown coefficients, often called generalized coordinates, are packed into a vertical column vector, which we label as a. Finding our shape function now requires us to determine the exact numerical values locked inside this unknown a vector. We solve for these unknowns by forcing our general polynomial to yield our actual physical nodal values at the boundaries. We execute our first substitution at node 1, where the spatial coordinate x equals 0. Plugging 0 into the polynomial collapses the equation. The a1 term vanishes entirely, proving a0 equals the boundary value, u1. Next, at node 2, we plug in length L, guaranteeing the function evaluates to our second boundary value, u2. By substituting our known coordinates, we have generated two simultaneous equations. These equations bind our generalized mathematical model strictly to the physical reality of the element's endpoints. To solve these simultaneous equations systematically, they must be structured into a unified matrix system. This reorganization creates a 2x2 grid of our spatial constants, known as the transformation matrix, or the T-matrix. The T-matrix acts as a mathematical translator. It directly maps our generalized coordinates, the a vector, to our physical nodal coordinates, the u vector. To isolate the a vector, we must move the T-matrix across the equal sign. Moving a matrix algebraically requires calculating its inverse. Multiplying both sides by T inverse successfully isolates the a vector on the left. Inverting the transformation matrix allows us to solve for the unknown coefficients. This provides the missing parameters needed to define the element's internal field based entirely on its boundary data. Let's bring back the original vector equation we established at the start. The continuous field U equals the spatial row vector H multiplied by the unknown column vector A. We can now swap out that unknown A vector with the inverted T-matrix system we just isolated. We multiply the H row vector, containing our spatial variables, 1 and x, against the constants inside the inverted transformation matrix. The algebra simplifies neatly, resolving into a single row matrix containing two distinct linear components, 1 minus x over L and x over L. These two resulting terms are exactly what we have been looking for. They are n1 and n2, the final derived trial functions or shape functions for this element. To prove that these algebraic functions work exactly as the Galerkin method demands, we must plot them back against our original physical boundaries. This 2D graph plots our first shape function, n1, over the spatial domain from x equals 0 to x equals L. The function starts perfectly at a value of 1 on the first node and slopes down linearly to hit absolute 0 at the second node. It exhibits strict compliance. N1 guarantees 100% influence at the first boundary and zeroes out completely at the second boundary, so it does not interfere. Adding the plot for our second shape function, N2, we see it starts precisely at 0 on the first node and linearly ascends to a value of 1 at the second node. The symmetry is perfectly engineered. N2 ensures absolute influence at node 2 while exerting zero influence over node 1. These highly specific individual functions can now be combined into a series format, ready to be processed by the weighted residual methods that govern finite element analysis. While modern software automates these inversions, this linear algebraic derivation is what enables a digital model to approximate a continuous physical field. It is the mechanism that translates discrete points into a coherent simulation of reality.